let's consider thermal conductivity and how it might depend on the phase of the particular substance. It turns out that there's actually a correlation between the phase and the thermal conductivity. Generally, as things are more in the solid phase, they're more conductive. When they're in the liquid phase, they're less, and gas phase even less. And this makes sense if you think about it, because in the solid phase, the constituent components, whether they're atoms or molecules, are close together and in contact and bonded together so that pulling on one transmits force directly to the other, and so any motion on the molecular level, which is what thermal energy really is, translates through the lattice pretty easily. So these vibrations move through it because the pieces are coupled together. In a liquid, there is some connection between them, but they're easily separated from one another, and so there's the ability to push and pull, if you will, through this. But in a gas, there's hardly any connection between the various molecules or atomic species, and so they hardly ever interact, especially if we're talking about an ideal gas, and they never interact. And so it makes sense that moving heat from one area to another, or moving thermal energy from one area to another, would be difficult. The only real way to do it is to get the entire gas to flow in bulk, but we're not talking about that. The gas or any fluid flowing in bulk it's given its own method of heat transfer. That's what convection really is. But conduction is just how much thermal energy will flow through a substance, where it's due to the interaction between the molecules. That's really what it is. So you see the logarithmic nature of the y-axis and how mostly gases are on the left and mostly solids are on the right. Now there's a nice table of thermal conductivity. Some of these I believe are apparent thermal conductivities. You might be surprised to notice that diamond is actually very thermally conductive. So if you take a diamond ring and perform an experiment with it, if you're allowed to, and you heat up one side of it, the other side will get hot very quickly. The thermal energy will transfer through the structure very, very rapidly. Silver is actually not quite as good a conductor. In fact, it's what, maybe 1/6 or so, 1/5 or 1/6 the conductivity of diamond. Copper is pretty good. There's no point in making our radiators out of silver. Oh, yeah, sure, it's more thermally conductive, but copper is pretty close and is a heck of a lot cheaper, of course. And so on. As we get down, we moved from solids now down to, say, mercury, which is liquid in this particular case, to water. You see that, between those two, there's a significant difference in thermal conductivity, but it's not the orders of magnitude difference that we see between solids and liquids. Now, of course, there's some solids in here. There's glass, there's brick sandwiched between the mercury and the water. So you can't say all solids conduct heat better than all liquids. That's not the case. There's some overlap, and you can see that if you look at the bars carefully and how they cover various ranges. There is significant overlap between, say, some liquids and some gases. This is more just a general trend. Now notice that glass fibers, for example, have a very low thermal conductivity, 0.043, but air has an even lower thermal conductivity. Now we make insulation for homes and buildings out of glass fibers commonly, and so it turns out that the glass fibers themselves are actually more thermally conductive than air. So you might say, well, why don't we just take the glass fibers out and let the air insulate? Actually, it is the air that serves as insulation. The purpose of the glass fibers is to hold that air still, because if the air is allowed to flow within the wall cavity, it'll set up a convection loop. It'll set up natural convection, and heat transfer will be enhanced through the wall. And so even though glass fibers have a higher thermal conductivity than the air itself, their job is to hold the air still so that the air serves as an insulator. And this is the case in rigid urethane foams, for example, where the really small gas bubbles within the foam are what actually provide the bulk of the insulation and the resistance to heat transfer. Speaking of insulation you might put in your walls, you might know that 2x4 walls, nominally really 1.5 by 3.5 inch walls, take R11 insulation, or even R13 sometimes, and 2x6 walls, or 5.5 inch deep cavities, take R19. And you might say, well, why don't you just buy the R19 and put it in the 2x4 wall? And that would enhance your resistance to heat transfer, right? Because it's R19, isn't it? Well, actually, the bat itself has to expand in the wall cavity. If it doesn't, if it's compressed, then because the glass fibers are more thermally conductive, it'll actually conduct more heat than the R11, or heat at a higher rate, I should say, than the R11 insulation would. So it's very important that these bats of insulation expand out properly. You don't want to stuff a wall cavity with insulation thinking that you are enhancing resistance to heat transfer. As a matter of fact, that's the way that these things are specified, right, is with their R value. So what do they mean by that? Well, if we know the apparent thermal conductivity K of the fibers, now understand when we say that, we mean not necessarily the fibers themselves, but how effective the fibers are at holding the air still so that the air behaves as the insulator. That can be worked together as an overall, if you will, thermal conductivity or effective thermal conductivity. If we know that and say it's 0.025 BTUs per hour per foot per degree Fahrenheit, you see it in the denominator there, then the thickness of the bat divided by that thermal conductivity is how you come up with the R value. So I did a quick calculation here just to show you how it works. So the thickness of this wall cavity is 5.5 inches because they're 2 by 6 walls. Converting that to feet, we'd have to divide by 12. So in the numerator, we have units of feet. In the denominator, we have the thermal conductivity, or essentially the apparent thermal conductivity. And so that's got units of BTUs per hour per foot per degree Fahrenheit. Now, units work just the same way as numbers, so invert and multiply that fraction in the denominator, and you'll end up with hours feet squared, because remember we had a foot in the numerator that matches or adds with, well, squares I guess, the feet in the denominator, and degrees Fahrenheit. So it's hours feet squared degree Fahrenheit per BTU. And it comes out to 18.3. My thermal conductivity may be a little off, or marketing may have got a hold of this number and just rounded it up to 9 for fun. But 19, R19, really means 19 hours feet squared per degree Fahrenheit, or degree Fahrenheit per BTU. Now, thermal diffusivity is a different parameter of materials than thermal conductivity, although it involves thermal conductivity. So if you look at the equation for thermal diffusivity, which is given the symbol alpha, really it's the ratio of heat conducted to heat stored. Now you might think about this and think, well, what is that supposed to mean? Well, I remember when I was working for Grody, there was this lamp they were developing. They already made some, but they called them buggy lamps. Turns out that Grody, although they make lights for the heavy truck industry, they also make lights that the Amish use on their buggies. I mean, think about it. A buggy, a horse-drawn buggy at night that's painted black. That's a really bad idea, right? Cars can't see you. And you may not know much about Amish culture. You may think that they shun electricity completely. They don't, actually. They shun connection to the world, and so they view the power lines or telephone lines as connection to the outside world. Ironically, they use cell phones, which is an invisible connection to the outside world, but that's their choice, their business, their beliefs. But they will use battery-powered stuff all day long. That's no problem to them because there's no physical connection to the outside world. So I guess that's where they draw the line. No physical connection to the outside world. Okay. So anyway, so Grody made lamps for this, this market segment, and the Amish would buy these buggy lamps, and then their buggies are safe at night. They were much better, obviously. Well, they were working on a new design for it, and the thing about light-emitting diodes you may not know is that they're not 100% efficient. About half, it depends on the die, but about half of the energy you put into the LED die itself goes out as light, the other half goes out as thermal energy or heat that has to be transferred away from it, otherwise the thing melts down. So they were working on a new design for these buggy lamps, and there was a big discussion between the machinists who were going to machine it out and the engineers who were designing it. And the machinist said, what we really need is a big block of aluminum on the back of this thing, because that would really suck up the heat. And the engineer said, no, what we need are fins. And both of them had a point. If you think about a big hunk of aluminum, that's kind of like an empty container just waiting to receive a fill of something, right? A fill of thermal energy. And so the aluminum, assuming that it has a decent heat capacity, could absorb that energy, but eventually what's going to happen is the temperature of the aluminum block will rise and the heat won't be able to get out of the LED, or the thermal energy won't be conducted away. And so the engineers were saying, no, we need fins on the back. And what the engineers were thinking was, we need to reach steady state where all of the thermal energy that's waste thermal energy is pulled away from the LED and then pushed out to the air or sent out to air. But that ratio of heat conducted, so through, versus heat stored, really is my point of this story. Now, if you ever go to a swimming pool in the summertime, you might swim in the top, feels nice and warm. You go down to the bottom, say it's a 10-foot pool, and it feels a lot colder, and you might wonder why. Well, there are a couple of different reasons, but one of the reasons is that water actually has a fairly low thermal diffusivity. Water has a fairly high heat capacity and a relatively high density, but its thermal conductivity is actually quite low. In other words, I could put a soldering iron, I could dip it into water here, put my finger right next to it, not touching the iron but touching the water, and my finger would be fine, because the water would not conduct the heat away very well. Rather, it would just store it. And of course, as it stores it, eventually it would have to change phase. I'm sure with a big enough soldering iron I'd be in trouble, but you get the idea, I hope. So water actually, if you notice the thermal diffusivity list there, water is pretty low on that list. Things like silver and gold, aluminum, they're high on the list mainly because they have relatively high thermal conductivities, K, and to calculate the thermal diffusivity, it's just the thermal conductivity K divided by the density of the material and divided by the heat capacity of the material.